So this is module 1 of psychological statistics 2. It is all about combinatorics and probability, but I had divided it into two parts. So this is part 1 that deals with combinatorics. So for combinatorics, we will discuss the following topics. The first one is on counting principle, and then we will talk about permutations, and the last is combinations. For the learning outcomes, after discussing this module, you are expected to learn how to count the total number of elements in the sample space and solve problems on combinatorics. So, what is combinatorics? In some other books, they call this as combinatorial analysis. So, it is the study of counting all the outcomes of some tasks, statistically called experiments. Sometimes these experiments are also known as probability experiments or simply experiments. So, these are chance process that lead to random outcomes. That is what is meant by experiments. When a particular experiment is being performed, then the results are known as outcomes. So, in the theory of probability, experiments are always correlated to the toss of a coin, the roll of a die, or the drawing of a card from an ordinary deck of playing cards. So, there are different ways of counting the total number of elements in a sample space. And one of those ways is the counting principle by means of the first one is counting by forming a list. So in short, gagawa ka lang ng listahan at sa listahan na yon, isasama mo lahat ng possible elements in included in the sample space. So for instance, your experiment is to roll a die. So what is a die? A die is that cubic figure with six faces, and those faces are actually represented by the number of dots. So if you're going to uh, transform those numbers into numerals, then we will obtain 1, 2, 3, 4, 5, and 6. So that represents the number of dots that can be seen on the uh, six faces of a die. So let's have this first example. One number is randomly chosen from the sample space S, which is equal to 1, 2, 3, 4, 5, 6, 7, and 8. By the way, sample space is a set, and algebra would tell us that a set is named using a capital letter such as S, and the members of the set such as this 1, 2, 3, 4, 5, 6, 7, and 8. These are called the elements of the set S. It is enclosed by the braces. This one, these are the braces. And these elements are separated by a comma. So that is how to properly name a set. So your task is to actually list the elements in the following events. Like the first event is the number is odd. So what is an odd number? An odd number is that number which is not divisible by 2. So looking at this set here, then we can list the odd numbers as 1, 3, 5, and 7 because these are the numbers that are not divisible by 2. In letter B, it says here that the number is divisible by 3. So again, we look back at S and we find 3 and 6 as the only numbers not or rather the only numbers which are divisible by 3. And finally, in letter C, you are asked of a number that is prime. So before we identify a prime number, you have to be sure that we know how to define what a prime number is. So a number is said to be prime if its factors are only 1 and itself. 1 is not included as a prime number because the smallest prime number is 2. So again, going back at the list, we can list 2, 3, 5, and 7 as the prime numbers. The rest are called composite numbers except one, which is said to be a special number. So, aside from counting by making a list, we can also count by making a table. So, this is true, especially if we're going to deal with a multi-stage experiment. So if it is a multi-stage experiment, uh, it has two or more sets of outcomes. Basic example would be the experiment, which is rolling a pair of dice. So when we roll a pair of dice, then there are actually 36 outcomes, and these outcomes are represented by this table. So for our column, we have 1, 2, 3, 4, 5, and 6 here. Again, just like in the first example, these are the number of dots that can be found on the different faces of a die. And this is die number 1 in pink, and the die number 2 is in bluish green. So the same representations for the number 1, 2, 3, 4, 5, and 6. So we have here for the first outcome, we have 1 and 1, meaning 1 on the first die and 1 on the second die. And then this one is 1 and 2, 1 on the first die and 2 on the second die. Here, this is 2 and 1, meaning 2 is obtained on the first die, and the second die, it has 1. So if we try to look at this one here, then it says that 4 on the first die and 5 on the second die. While in this result here, this is 5 on the first die and 4 on the second die. So if you try to count, these are equivalent to the 36 outcomes if a pair of dice is rolled. So from the table about the 36 outcomes, when a pair of dice is rolled, you are asked to list the elements of the following events. So the outcomes of an experiment is known as events. So let's say that the first event is to come up with a number with a sum of 9. So our sample space is represented by set S, and we do it this way. It says here that the sum. Oh, so a sum is the answer for addition. So we try to look at the pair of dots that give us a sum of 9. So what do we have? We have 3 and 6. We have 4 and 5. We have 5 and 4. And we have 6 and 3. So from the table, we can make a list such as this one. Or what if the event is a sum which is less than or equal to 5? So in our mind, we think of the sum, which can be 2 or 3 or 4 or 5, because these are the only sums that will satisfy the condition that it should be less than or equal to 5. So we get a sum of 2, we have 1 and 1. A sum of 3, This is a sum of 4, sum of 5, sum of 5, 5, and 5. So all of this represent the event here. In the third example, we have the event is to obtain a sum greater than 12. So if you try to go back at the table, you can see there that the highest sum would be 12. So that it would be impossible for us to obtain a sum greater than 12. So kung titingnan mo yung S dito, it is represented by a null or an empty set. So this is what a null or empty set looks like. The fourth example is to get a sum that is a prime number. So earlier, we had defined a prime number as a number whose factors are 1 and itself. So if you try to enumerate, the smallest prime number is 2. So we have here a sum of 2. And then the next pair would be a sum of 3 because 3 is also a prime number. So as with 5 and then 7 and then 11. Although we can also enumerate other prime numbers, but the table are revealed that the highest of the sums is only 12, and 12 is not prime, so we have here the last pair of sums would be the sum of 11. And finally, the last event would be a sum of 12. So again, go back to the table and that you can see there that the highest sum is 12. And there is only one pair. 6 on the first roll and another 6 on the second die. So we only have one element that is 6, 6. So that is how to make use of a table on listing the elements of a sample space. The third method is to count by using a tree diagram. So a tree diagram looks like this one. The problem here is to count the total number of possible outcomes when a coin is tossed 3 times, or if you are going to toss 3 coins. So for the first toss here, then you can have either a head or a tail. In the second toss, the same event will come up, either head or a tail, head or tail. But there is another toss with the same event. So if you try to start with the H here, followed by an H here and another head here, so the first outcome would be 3 heads represented by H, H, H. So meaning to say that head on the first toss, head on the second toss, and another head on the third toss. For the second event here, or the second element would be H, H, and T, meaning head on the first toss, head on the second toss, and the last toss is tail. And the rest follows. So if you're going to toss a coin 3 times, then there are 8 possible outcomes represented by the combination of heads and tails in here. And then, aside from that, you can also count the total number of possible outcomes by making use of the counting principle. So, sometimes this is also known as the multiplication rule and represented by the MN rule. So, when we speak of the MN rule, this is just simply the product of M rather, times N. So, simple multiplication. Example, how many two-letter word with or without sense can be formed using the letters R, T, and U when repetition is not allowed. So following the MN rule, M is equal to 3. Why 3? Because there are 3 letters involved, R, T, and U. What about N? N then becomes 2. Why 2? Because it says here that repetition is not allowed. Meaning, if you had used uh, one letter for M, then that letter cannot be used for N. So you only have two choices left. Sabi kasi dito, repetition is not allowed. Ibig sabihin, bawal kang mag-ulit ng mga letters. So, 3 times 2 is equal to 6. And you can list all those 6 elements as RT, RU, TR, TU, UR, and UT. These are the 6 elements of the sample space. Aside from that, we also have the extended MN rule, that is, if a particular experiment involves not only two stage but rather more than two stage. So we have here an example. If you have shirts and 5 skirts, 3 sneakers, 4 hats, the question is, how many outfits consisting of a shirt, a skirt, a sneaker, a hat can you make? So, kunyari gagawa ka ng OOTD na ito yung bubuo sa OOTD na yon. So, this is an extended MN rule. So, kanina meron lang tayong M times N. So, ngayon meron tayong M times N times O times P. So, simple multiplication, 8 times 5 times 3 times 4 is equal to 480 outfits. Ito yung ibig sabihin natin ng counting principle. The next one would be about permutations. So, before we discuss permutations, we will discuss first factorial notation, because in the formula of the permutations, the factorial notation is actually included there. So when we speak of a factorial notation, it is simply the product of integers from 1 to n, where n is the given number. The factorial notation is represented by an exclamation point. Like 5 factorial, if we follow the definition of a factorial notation, so our n is represented by the 5. So it is just a product of integers from 5 or from 1 to 5. Or you may also do it the other way around, 5 to 1. Anyway, multiplication is commutative. So we have 5 times 4 times 3 times 2 times 1, and the product is equal to 120. So that's how factorial notation works. And by the way, in this topic, this is psychological statistics. As mentioned in our FB group, you are required to have a calculator, and as much as possible, it should be a scientific calculator so that it would be easier for you to calculate permutations, and then later you will have combinations and also factorial notations. In your scientific calculator, simply look for the N and then exclamation point, or sometimes it is also X and then the exclamation point. So you will simply press 5 and then that X factorial, and right away the answer, which is 120, will be given to you. So as easy as that if you have the calculator, the scientific calculator. So for the permutations, we have here the formula. But before that, we define permutations as the arrangement of n different objects or n distinct objects where order is important. So here we take notice of the objects that they should be in particular order. So permutations are all about arrangements in particular order. So the formula is given by NPR. NPR is read as the permutation of n different things taken r at a time, which is equal to n factorial divided by the quantity n minus r factorial, where n is a number, r is also a number, and r is always less than, if not equal to n. So let us have these exercises. We have 7P3, we have 9P2, we have 6P4, or this is read as the permutation of 7 different things taken 3 at a time. So for our solutions, we have here, since according to the formula, it is equal to n factorial divided by n minus r factorial. So n is equal to 7, 3 is equal to r. So that the permutation of 7 different things taken r at a time is equal to 210. So by the way, NPR, or the formula for the permutation, is also included in your scientific calculator. So simply look for it. If not in the first function, then perhaps you need to press the shift key for the second function for you to answer problems about permutations, so that you will no longer do it this way, but simply make use of 7 and then press the NPR key and then press 3 and then press the equal sign, and you will be given 210, and so on and so forth. So these are the different problems concerning permutations. So your clue here is that in a particular problem, there should be a word or a group of words there that suggests a particular order. So an example would be a table tennis team consists of 6 players ranked from 1 to 6. So if there are 10 players from which to choose, how many different tennis teams can the coach select? So here, the clue that uh, a particular order is to be followed is that there is a particular rank here, rank from 1 to 6. So that our n is equal to 10 and r is equal to 6. So the permutation of 10 different tennis teams chosen 6 at a time is equal to 151,200. So aside from that, permutations can also be applied as regards to identical objects. So when we speak of identical objects, these are objects that are the same. So usually examples in these objects are represented by a word with uh, the same or identical letters, or maybe problem concerning colors, where different colors are involved, but of course these colors are also identical in some ways. So example, this is a permutation with identical objects. So how many arrangements are possible using the letters in the word Mississippi? So it is the same as n factorial over n sub 1 factorial, n sub 2 factorial, and so on and so forth. So, or you may represent the denominator as k here, so that it will be different from the n, where n is the total number of letters in the given word. So the word is Mississippi, so we count the letters, we get 11. K sub 1 would be represented by the letter L. Not L, but it is the letter I. Sorry for that. So the letter I, so we count the letter I's here. And then K sub 2 is equal to 4 for the letter S. And then k sub 3 is equal to 2 for the letter P. And then we apply the concept of factorial notation, the one discussed earlier. So it is equal to 11 factorial divided by 4 factorial divided by 4 factorial divided by 2 factorial divided by 1 factorial. The total is equal to 34,650 arrangements. So by the way, the sum of the denominator here, 4 plus 3, 4 plus 4 plus 2 plus 1 is also the same as our numerator, which is 11. Oh, another example would be how many arrangements are possible in the letters of the word psychology. So we count the number of letters in psychology. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So that would be equivalent to 10 factorial. And then the second would be the letters which are repeated. So we only have the letter Y. So we have two Y's and we have two letter O's here. And the rest, they appear only once. So we have a total of 907,200. Please check using your scientific calculator. We also have what is termed as permutation. So this one is easier because the problems here would have something to do with uh, anything that is circular in shape. It always referred to an object which is circular. So example, in how many ways can 9 people be seated at a round table? So the object that is circular here is the round table with 9 chairs. So here, it is equal to n minus 1 factorial. That is the formula. So if n is equal to 9 minus 1 factorial, so we get 8 factorial. That is equal to 40,320. And the last part would be about combinations. So just like permutations, combinations are also arrangements. The only difference is that if it is a combination, then the order is not important. The formula is NCR. It is read as the combination of n different objects taken r at a time, which is equal to n factorial divided by r factorial times n minus r, the quantity of n minus r factorial. So again, both n and r are numbers, number of objects, and then the value of r is always less than the value of n. So here are some examples. Just like the NPR or the permutations, there is also a key for the combination in the scientific calculator. All you have to do is to press N, N that stands for the bigger number, and then press the key for the combination, and then press the key for the other number which is represented by the R, and then press the equal sign, and you already have the answer for the combination. So these are our examples. We have the combination of 10 different objects taken R at a time, or the combination of 20 different objects taken 6 at a time, and the combination of 18 different objects taken 10 at a time. And number 4, we have to count first the number of letters that represent education. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So n is equal to 9, taken 3 at a time. So we have here the answers. So you may check using your scientific calculator. So in number 4, 9 is our n, r is equal to 3. The combination of 9 taken 3 at a time is equal to 84. So there are 8 possible combination using the word education taken 3 at a time. So the next set of examples would be in how many ways can 5 representatives be chosen from among 50 students? As mentioned earlier, Both N and R are numbers. N is always the bigger number. So there are 50 students. And from the 50 students, you're going to choose five representatives. So in how many ways can you choose these five representatives out of the 50 students? So we have here. It is equal to 2,118,759 ways. In number 6, so this is a popular example where we can use combination in terms of lotto. So lotto is an example of combination or problems rather concerning combinations. So here we have the mega lotto and we will have the ultra mega lotto. So only those who are uh, perhaps fond of betting in a lotto can understand what a mega lotto is and what an ultra mega lotto is. And number 7 here, we also have a problem with about five psychologists and three psychometricians, and you have to choose them from a group of eight psychologists and five psychometricians. So we have here the solutions for the mega lotto. There are there are 49 possible numbers, and from here we can choose six numbers at a time. So by the way, I am also not a better of lotto, so please check if it is if there are 49 really 49 numbers that can be chosen from. And the last one is the ultra mega lotto. You have to choose six numbers from a total of 58 numbers. So if you have to buy one ticket or choose one combination, and then you have a total of 40,475,358 combinations in all. So, kumbaga, kung tataya ka, tapos nag-iisa lang yung ticket na tinayaan mo, then mananalo ka ba? So, yung chance na mananalo ka, 1 out of 40,475,358. And finally, the last one is the number of possible ways you can choose five psychologists from a group of eight and three psychometricians from a group of five. So we have 560 ways. So these are the references used for this particular topic. Thank you.